Good morning, and I'm glad you're here. Thank you for coming. You're looking at the final presentation for Archangel Defense Systems. They're going to talk about their YB-25 Spectre. I will let the program manager, Josh Waltz, introduce his team. I'd like to introduce our distinguished panelists.
Okay. I'm Bill Zwick, retired Raytheon and faculty at Embry-Riddle.
My friend Scott Wells.
Scott Wells. I'm an 87 Embry-Riddle grad from this campus, and I currently work at Raytheon Missile Systems. I do flight controls, autopilots for missiles.
Garrison is one of our most faithful reviewers. He comes all the time. We're glad he's here.
Yeah, I graduated in 2015. Currently work at NOC-WD, and I worked on propulsion systems, electro-optical systems, and civilian control.
With that, you guys take it away.
Hi everybody, as Dr. Crisler said, we're Archangel Defense Systems, and this is our project, the YB-25 Spectre. So our team is Michael Aki, Nicholas Arnold, Brian Cowley, John Marvitt, Van Pollard, Caitlin Sjostrom, Max Starkle, Rand Van Sickle, and I'm Josh Waltz.
And our distinguished reviewer, Steve Robinson, is with us. He's from NASA Armstrong, which used to be NASA Dryden, now at Edwards Air Force Base. There you go.
So this is the layout of our team. At the top we have Dr. Crisler. He's the management and the customer, playing both roles. I am the program manager, as Dr. Crisler said. Max Starkle is our chief engineer. And we are broken up into 8 IPTs. We have the ERAU, propulsion, civilian controls, structures, weight and balance, performance and requirements, systems and crew, and CAD IPT. Our requirements are aircraft is supposed to replace the B-2, the B-1, and the B-52, and account for the shift to Southeast Asia operations in that region. So we came up with an RFP that outlined these requirements. We needed an unrefueled range of 8,000 miles. I forgot to mention, the threshold values are our minimally compliant values, and the objective values are kind of goals that we wanted to achieve. So for unrefueled range, we wanted 8,000 miles, and this was based on coverage from Guam and Diego Garcia. Payload of 40,000 pounds, and this was driven by several of our payload packages and the rotary launchers and the racks. The takeoff length of 7,000 feet was supposed to be comparable to the B-2, so we were operating from the same airfields as the B-2 currently operates from. The cruise Mach at 0.8, a cruise altitude of 40,000 feet, a service ceiling of 45,000 feet, and because we are a nuclear capable bomber, we need to handle 2 engines out on the same side and handle crosswind landing of 30 knots and a G limit of 3, and we imposed a factor of safety of 1.25. This map shows the range. It's a 4,000 mile circle from Anderson Air Force Base in Guam and Diego Garcia, and this shows that we can cover almost all of Southeast Asia from these 2 locations. We won't be really taking off from those 2 locations that much, so we plan to start off at Whiteman Air Force Base, similar to the B-2, and we would either refuel over Edwards Air Force Base or Hickam Air Force Base in Hawaii, and then continue on to Anderson Air Force Base in Guam. And from there we could also go to Diego Garcia, but either way we could cover most of our combat area in that from those 2 points. This is a 3 view of our aircraft just to kind of show you the general layout. We're going to go into the specifics during our presentation. Just wanted to show you a general overview of it. This is how it compares in size. These are all scaled drawings of our comparable aircraft, the B-2, the F-111, and the Avro Vulcan, just to show how we measure up against those so that we're within the range of reasonable sizes. This is our constraints diagram. This is how we entered the design phase. As you can see, we're the star there. We are not quite in the design space that we wanted, which was down here. This is the minimally compliant range. If we had to go through a couple more iterations, we would definitely drive that down. But right now, we're at a wing loading of 64 pounds per square foot and a thrust to weight of 0.28. This is pretty similar to the B2 and in the same general area as the Vulcan and some of the other comparable aircraft. And now I'll hand it off to Max for the internal arrangement.
Okay, so shown above is a general overview of the bomber. If you guys can see very well up there, one in front of you, it's up here too. Basically how it works, because we wanted to do a stealthy design, we don't have any sort of tail structure. So to compensate for it, we have 3 different control surfaces on each side, 2 elevons and split drag rudder flaps over here on the edges. And then main structural members, how it goes, the wings are all composites, main structure is aluminum. We ran a keel down the center for conventional design. We have 2 bomb bays similar to the B2. We have ducted engine interface for, again, stealth purposes, hide the engine interface itself. Cockpits, it's 2 pilots. We have directed energy weapons in case you run into any defenses. Of course, so you want to be stealthy, but just in case. We also carry other defensive countermeasures such as flares, and fuel is basically the rest. So this video shows the opening the doors on the bottom. So 2 bomb bays that open there and the bomb falls out. We have the engines access, so if you ever need to do maintenance, you can drop them at the bottom. Main landing gear doors and the nose gear doors. This is an example of one of the different packages that we can carry for our payloads. So what we decided to carry 45,000 pounds of payload. What that gave us was as many different packages as we possibly could carry. On the left, we show a different ordnance that we can carry based on number and weight and size for either rotary launcher or conventional racks. On the right are different strike packages that we think in theory could be applied, ranging from coastal strike all the way up to nuclear, conventional bomb strike, or hardened target penetration. And next I'll hand it off to John for low observables.
Thanks, Max. So to improve the survivability and effectiveness of the aircraft in the danger zone, we wanted to incorporate some low observabilities into our aircraft, or some low observable qualities to our aircraft. We did a lot of research on this subject, came up with these kind of rule of thumb ideas. We made mostly the illumination of all 90-degree angles. We wanted to also increase or provide a really smooth surface so we don't have any surface discontinuities. Messed up the inlets, so we'd be hiding the compressor face. Special coating over the cockpit windshield so that radar wouldn't penetrate, reflect off the inside of the cockpit. As far as materials go, we were looking at using RAM and brass. So the RAM would be incorporated into the paint. The brass would be a part of the structure, modifying the leading edge of the aircraft. For infrared detection, we are using a square nozzle in the back. This should encourage the mixing of hot exhaust air and cold atmospheric air. Additionally, we're looking at using zinc sulfide to force infrared radiation into a wavelength that doesn't transmit as well through the atmosphere. And now I will hand it off to Michael to do aerodynamics.
Thank you, John. The first thing for aerodynamics was we needed to pick an airfoil that could delay the critical Mach number over the wings as far as possible, as well as give good performance characteristics such as high CL and a low CD, and as well as have enough volume in the wings when transferred to 3-dimensional in order to hold subsystems like fuel and electronics. Overall, what came up was the Wortmann FX80080 airfoil, shown on your left here. This airfoil with an 8.1% thickness ratio, coupled with a 40-degree leading edge sweep, gives our wings a critical Mach number of 0.83. As you can see, the 2-dimensional data here, this is derived from X-Flag 5, just using 2-dimensional data for airfoil tools, and will be converted into 3-dimensional data using Brandt's methods. Once that 3-dimensional data was converted, it also needed to be reconverted again to give us a blended wing body sort of estimation, since our aircraft, as you've seen, is a blended wing body design. The blue line above me here shows the overall aircraft with that Brandt's transformation for our clean aircraft. The orange line above it shows our dirty configuration on takeoff and landing, which is all of our control surfaces deployed 30 degrees downwards, and has all 3 segments on both wings deployed. Overall, with our clean configuration of our aircraft has a max CL about 1.2 with a stall angle of just above 11. When the flaps are deployed, the CL max jumps up to just below 1.6 and delays backwards to under 10 degrees. So same with the drag polar. This is again using the Grant's methods of blended wing body. The blue is clean. Orange here is the dirty configuration. The bottom here, as you can see, shows the breakdown of the drag on different components of the aircraft, body, wings. The delta is any irregularities over the surface of the aircraft, such as the cockpit, bump, the inlets, such as that. And of course, the landing gear and flaps drag is only for takeoff and landing situations, again at the 30-degree deflection. Overall, in flight, we have sea level and cruise condition at 40,000 feet displayed up here for our L over D. Overall, our max L over D for the YB-25 can achieve 23, but our cruise condition, which is a velocity of Mach 0.8 at 40,000 feet, is an L over D of just under 23. I know I said before that the critical Mach number over the wings is Mach 0.83, but the thickness with the length of the body, as you could have seen before, reduces the critical Mach number over the body to about just under 0.82. So we set the cruise velocity to 0.8, just so that our aircraft does not get into the transonic region and experiences any wave drag. Oh, and our Reynolds number is in flight, technically is 95 million, and that will come into play later when our wind tunnel model is created and tested. So a bunch of us have never really done any blended wing body designs since in our college career. So we had to see if our numbers and assumptions actually made sense and could produce actual values. So we compared our tool validation to the Avro Vulcan and the YB-49 to fairly blended wing body designs similar to our own, and that has public information that is out there. Overall, as you can see from both YB-49 and Avro Vulcan, the main characteristics, we have a max error of just above 5%, which is very acceptable for our calculations. But first we need to start moving forward, so I'll give it to Josh for propulsion.
So we decided to select our engines based on one at low TSFC and a thrust to weight that's similar to our comparable aircraft. Using this data, we ended up with the engines shown here on the right. We excluded high bypass ratio engines because of the S-ducted inlets. They can cause pressure variations that will cause the engine to tear itself apart, which is a bad thing. So we ended up with these engines from the F-15, the F-16, the B-1, the B-2, the F-22, and the F-35. We considered adding on afterburners and doing water injection and taking off without full fuel weight because we are a fairly heavy aircraft, but we ended up not really needing any of that because we reduced the weight down at the beginning of this semester. So we ended up choosing the F-101, 102, a derivative of it. We updated it with current technology levels. We ended up with a sea level thrust of just under 20,000 pounds and a TSFC of 0.56. This picture here does include the afterburner. This was removed for our use, and we estimated the new length and weight of the engine based on other engines that don't have afterburners. And yes. So these are the performance predictions of our engine. As you can see, the TSFC increases with Mach number and throttle ratio and decreases with altitude, and the thrust also decreases with altitude, which is all fairly expected. It just kind of shows that we're on the right track with these predictions. From there, we sized the inlet and the diffuser. The inlet was sized using the PERF program, and it was found that we needed just under 10 square feet for our cruise condition, but we upped that to 10 square feet just to kind of handle the takeoff and landing conditions a little bit better. The S-ducting of the diffuser, it hides the fan face, as John said before. We are going to implement turning vanes to kind of limit the pooling and directionalize the flow a little bit better. And as an added benefit, those will hide the fan face even more, which will reduce our radar cross-section even more. The offset is not a risk based on the AIAA paper on diffuser design. As you can see, we're right on the edge of the well-established region of data, so we should be fine, and that's not a risk of the program that we expect to have. We will need blow-in doors on takeoff, and these were sized using the PERF program as well. The nozzle was again sized using the PERF program and was found to be about 7 square feet. per side, or per engine, excuse me. And they were designed to be similar to the B2 nozzles to reduce the thermal cross section. They were rectangular to promote mixing with the cool ambient air, and it's on top of the aircraft to hide the hot air from view from the ground. The bypass air from the engine also helps cool the exhaust, which is an added benefit of the turbofan engine. We are also including inlet guide vanes similar to the diffuser on the nozzle, just to help with the pressure recovery in the nozzle. And I will hand it back to Mike for performance.
Thank you, Josh. Here we have our piece of best diagram starting at 5,000 feet per minute, going all the way up to 0 feet per minute. The star denotes our cruise condition there at 40,000 feet and just at Mach 0.8. Our service ceiling overall is just below 46,000 feet, and our absolute ceiling is at 46,600 feet. Our piece of best lines do go above Mach 1 as shown there, but when doing these calculations, we did not put into consideration the Q limit and the max forward speed that the aircraft could achieve, which is why the red line is there. That shows the maximum velocity at cruise condition of 40,000 feet. Again, with the thrust available, thrust required here, both callouts on the left and the right side here show the minimum velocity and maximum velocity at the current altitude. This one is currently at sea level, and the massive rise here in the thrust required is due to the wave drag over the body. So moving on, here we have our cruise condition at 40,000 feet, same thing. The envelope does close, the lower limit of Mach 0.41, the upper limit of 1.08. Again though, during the calculations, we did not put in the Q limit, so the maximum velocity at cruise condition at 40,000 feet should be just below Mach 1 at about 0.98. One more, at our service ceiling, 45,000 feet. As you can see, again, the envelope gets smaller and smaller, and the drag rise is due to the wave drag from transonic region. It should also be noted from all those graphs, the airplane was at full fuel and full payload. So here we have our range and endurance diagrams. There are different payload options here that we have. Of course, as mentioned before, our aircraft can hold a maximum payload of 45,000 feet. So with that payload and our max fuel, we can have a max range of just under 9,000 miles and an endurance of just below 17 hours. In case our aircraft wants to do more of a reconnaissance or electronic warfare, our payload of 0 in just the bomb bay compartment, our max range goes up to above 10,000 miles and a max endurance of 19 hours. But if there are no bombs in there, we can put external fuel tanks or additional fuel tanks, equaling out the max payload of 45,000 pounds. With that, ultimately, with the extra fuel, we have a max range of just under 14,000 miles and an endurance of under 26 hours. Our aircraft can hold a max fuel weight of 112,000 pounds without the extra fuel tank. Excuse me. So we have to get off the ground first. Using Nikolai's methods, we have our takeoff analysis. He breaks it down into 4 different distances: the ground roll, the transition, the rotation, and the clearance. We are using the standard 50-foot obstacle at the end of the runway for military aircraft, so that is taken into account. They are broken down above me here for their different distances, but overall, on a dry runway with full fuel and full payload, we do have a takeoff distance of just under 5,900 feet, and that is compliant with our total takeoff distance of 6,500. With full payload and full fuel, our stall velocity goes up to about 182 feet per second, which is just around 110 knots. But using the standard 1.2 factor for takeoff velocity, it brings us up to 220 feet per second, which brings us to about 120 knots. So after the mission is over, we have to land, hopefully in one piece. Again, using Nikolai's method, he breaks it up into 3 different distances: the air distance, the free roll, and the braking distance. Once again, they're broken down for you individually at the bottom, but overall, our aircraft has an approach angle of just under 3 degrees and a total landing of 3,400 feet. This is also compliant with our 3,500 feet landing distance. Nikolai does assume that the aircraft is at half fuel weight, just in case the mission is aborted mid-flight, or that the target area is not at our maximum range. So that is what these calculations are done at. With the half fuel, the stall velocity of the plane with a max payload, in case we didn't drop any, is 162 feet per second, which is about 95 knots. But with the standard 1.15 factor of safety for touchdown velocity, that brings us up to 186 feet per second, about 111 knots. This is our maneuvering diagram. The red box here shows what our aircraft is capable of. The top red line here is the noted before, the 3G limit that our aircraft can pull. The right line is the maximum Mach number at cruise of just under Mach 1, 0.98, as I mentioned before. And the left is the stall limit, where our aircraft is going too slow with the max fuel and max payload, and will begin to fall out of the sky. But first, to hold all those weights, hand it off to Rhiannon for structures.
Thank you, Mike. So for the materials of our aircraft, we chose to use aluminum and carbon composite. Our carbon composite is called the Perseus composite and is currently under development by NASA and about at the TRL level of 6. We chose this due to its lightweight and high strength properties, radar absorbing properties, especially for the skin. And since the Perseus composite is a stitched composite and has damage resistant properties, we selected aluminum due to its predictable behavior. And since the body of our aircraft is a little more complex, carbon wouldn't be necessarily the best choice for this. In between the aluminum and the carbon composite, we have a single layer of fiberglass between to avoid galvanic corrosion. For our wing design, we have 2 I-beam spars located at 15 and 60% apart. We have 16 ribs located throughout the span of our wing, and they're spaced for control surface sizing. I placed 6 stringers throughout the cord of our wing to reduce our wingtip deflection and apply a lift distribution with 3G loading at a 1.25 factor of safety. For our finite element analysis, we achieved a stress singularity in the middle of our, I'll start with the boundary condition. So I applied a fixed boundary condition at the root and applied the Schrade's lift distribution across the span of the wing at each spar location along at each rib location along the spars of the wing. We achieved a stress singularity in the middle of the wing due to the loading and geometry, but since this is so far away from the root of the wing, which is the actual area of interest, it can be ignored. The max stress achieved at the root of the wing is 161 KSI, which is below our allowable stress and yields a margin of safety of about 8.7%. For our wingtip deflection, during ultimate loading, our wingtips deflect about 21 feet and in flight about 7 feet, which sounds like a lot, but compared to commercial composite aircraft and other metal bombers, this is similar. However, this will require a lot more investigation to see how this affects our stealth characteristics, our control surface effectiveness, and aerodynamic characteristics. So that's a topic for further investigation. For our body design, we also analyzed for 3G loading configurations. Our frames are spaced for our bomb bay and our engine placement. And the bomb bay within the frame is 6 feet by 6 feet and 21 feet long and can hold 45,000 pounds. We performed gust loading analysis and determined that at lower altitudes it does not affect our flight envelope, and at our 40,000 foot altitude it doesn't exceed our 3G design limit, so gust loading wasn't a factor in our analysis. And now I'll pass it out to Kate for a subsystem or subscale model.
Thank you, Rhiannon. So in order to test the lift, drag, and yaw control on our aircraft, we designed a subscale model that had interchangeable wingtips so that we could test multiple flap configurations. We had a clean wingtip, and we tested both upper flap deflection and upper and lower flap deflection at 30 degrees and 45 degrees. Our model was 1:66 scale, but it had to be cut into pieces in order to be 3D printed. We cut off the wings and cut one wing in half so that it would be interchangeable. We also had to cut the body into 2 pieces in front of the inlet in order to fit the requirements for 3D printing size. The model was reassembled using steel beams in order to make it structurally sound so that it can stand up to the forces experienced in the wind tunnel. The wingtips were screwed on so that they could be removed easily during the test. The other pieces were all glued on so that they would stay together. And now on to John for wind tunnel testing.
Thank you, Kate. So as was mentioned before, we looked at 2 different subjects for our wind tunnel testing. The main subject was actually functionality of that split drag rudder, just because there's not a lot of data out there regarding how they work or how effective they are. We were concerned not only with the yaw moment that would be produced, but also with the moment coupling produced in the roll direction specifically. The performance data was collected as well. We'll go over that later. For the controllability, we were primarily concerned about landing in the 30-knot crosswind, just because we didn't have a lot of data about the yaw controllability of our aircraft. We did the math, and that came out to about 8 degrees of beta in the wind tunnel. So we evaluated at the landing, which is 3 degrees, and at takeoff, which is 8 degrees, as well as a 0 degree angle of attack. Before we could start testing, we actually had to develop a calibration curve for the potentiometer attached to the yaw controller in the wind tunnel. So we took a bunch of data points for a bunch of displacements of a long bar placed in the wind tunnel and developed this calibration curve. Used this to set our yaw angle more accurately than what had been done in the past. The performance data, it doesn't match up very well. This could be due to a number of factors. We're not, primarily probably the Reynolds number issue. We were testing at 130,000. As Mike mentioned earlier, we fly at 95 million. It's a pretty big jump to try to correct for. Not a lot we could do with that, but we tried our best. For the controllability stuff, we looked at first the drag that was produced by deploying these flaps, just to see what kind of drag increase we saw throughout all of our testing. Obviously it worked. We did see a drag increase. The 45-degree full deflection showing the most increased drag. For the moments, this is just the worst case scenario for us. So flaps were deployed on the left-hand side, and this is the beta of -8, so the right wing was forward. We would expect to see a decrease in efficiency on the left wing, but we're still generating a negative yawing moment. These trend lines here aren't so much trend lines as they are to guide kind of your eye. So you can see data points here, here, here. But at that negative yawing moment, we would have expected to see kind of a positive yaw. We can do with no control surfaces here. But since we are generating a negative yawing moment, we are controllable. For the moment coupling, it's kind of, again, unpredictable. We do see that coupling. We did expect to see some coupling, but there's really no way for us to model this. We need to do a lot more testing to kind of validate what those control surfaces are doing exactly, especially at a high sweep angle. And I will hand it off to Brian to talk more about stability control.
Thank you, John. So at the beginning of our stability control program, we started sizing our control surfaces based off of historical data. As you can see, there are 2 clusters of data points for our comparable aircraft. There are the older designs, the legacy designs, and then there's more recent designs like the B2 and the X-47B. As you can see, our design of 35% chord and 65% span is around the center of the design range. And thus, our control surfaces were sized. We have 2 types of control surfaces, elevons and split drag rudders. And the elevons on one side comprise of about 66.6% of that side, and the split drag rudders 33%. All the control surfaces can deflect to a maximum angle of 60 degrees in both directions. And this is a visual example of our control surfaces. So, as you can see, split drag rudders open. They can open independently between the sides. They can open independently on the same side and rotate. And then, for our elevons, similar thing. Both can deflect. They can deflect independently across the sides and on the same side for maximum controllability. So, this brings us to our high stress case scenarios. There are 3 scenarios of concern for us, which are crosswinds on landing, high altitude, and engine out on takeoff and landing. And the YB-25 can handle all of these. For a crosswind on landing, we only need 36.6% of our control authority. And then for our high altitude control, this was the most limiting case. So when we deflected all of our control surfaces, we were able to adhere to the mil-spec requirement of rolling 30 degrees within 1.5 seconds. Because we are minimally compliant with this, our control surface sizing is minimally compliant and is the smallest size, both in terms of area coverage on the wings and in terms of deflectability, in terms of how far they can go up and down. And then for the engine out of takeoff, we just need 29.2 degrees of split drag rudder in order to counter. So in terms of our longitudinal stability, in terms of our sag margin as percent MAC, we never crossed the 0%. So we are statically stable in pitch throughout the entire mission under any single type of payload configuration that we choose to carry. In total, we have about an 8% static margin shift, as you can denote by this image, where the blue is the most forward and the green is the most aft. Because we only shift about 8%, this means that there is less work that has to be done on our flight control computer in order to effectively operate the aircraft. So, in terms of our static stability criteria, these are our analytical solutions to our static stability. And what we found using our analytical approach from the US Air Force's stabilitycontrols.com and a few modifications due to our tailless design is that the YB-25 is unstable in yaw due to side slip. And a lot of the other characteristic parameters are outside of the typical range that you would expect for conventional aircraft, but this is understandable because we are not using a conventional design. However, this does show that our aircraft does have a need for a flight control system. So we designed one. It's quadruplex redundant due to our nuclear capabilities. So we have 4 sets of flight sensor data, which feed into 4 different flight control computers. And those flight control computers feed into 4 remote actuation terminals. We chose an actuation terminal design due to saving wire, using wireless. And then each one of those feeds into 2 sets of actuators per control surface, such that if one set of actuators were to fail, the others would be in complete control authority over that same control surface. So to do this, we need a set of flight sensors in order to denote crucial information to our flight computers. So we are going to be using a series of inertial navigation units, which will be placed under the cot in the cabin, and a series of static ports, which will be placed on the nose. The static ports will be very small in order for it to not affect our RCS by a significant portion. Now, using this flight system and using our analytical solution with the US Air Force's DATCOM, we were able to run our numbers through a 6 degrees of freedom simulation in simulating what our aircraft would actually do. And it was found that we were able to find a control solution that would give us level 1 flying qualities for our class of aircraft. As you can see, the pilot need only give simple stick commands in order to produce nice, clean, modified results for our control surfaces in order to produce nice, good responses. Now, the takeaways in terms of stability and control from our wind tunnel testing is CM beta from our criteria, our analytical criteria, needs to be negative in order for us to be stable. And as you can see, we do have this nice negative slope from about -5 degrees angle of attack up until about 9, in which we become unstable in the stall region. Now, we would never reach this particular point in our flight envelope or our flight patterns because this is around the point where our engines would blank due to flow separation. So we are stable under all flight conditions. In terms of the roll stability, however, the wind tunnel results were a little more ambiguous. As an angle of attack of about 0 degrees, we get that same nice negative CL beta curve, but at higher angles of attack, the results can be more ambiguous, showing marginally stable results or even unstable. But these were so skewed and ambiguous that we really need more investigation in order for more project to move forward. And then finally, in terms of yaw stability, we learned that we are stable with a nice negative slope under all flight conditions, even when we do not have any split drag rudder deployed, which was a relief for us. And now, hand it off to Nick for weight and comments.
Thank you, Brian. So this first table shows a breakdown of all of our component weights and also our component numbers, and then sums them up to our total max takeoff weight of 284,300 pounds. We compared our rate fractions against those of the B-2 because it was our closest comparable. As can be expected, given our longer range mission over the B-2s, we have a higher fuel fraction and a lower structure fraction. What's interesting to note is our payload fractions for both expendable and fixed payload increase. This is largely due to the overall decrease in weight of our aircraft, as well as the addition of the directed energy weapons for our defensive capabilities. I will now continue on to talk about systems and crew, and starting with the landing gear. For our landing gear, we decided on a 90-10 loading ratio. This was to pull as much weight off of our nose gear, which was experiencing extreme loads in an emergency braking scenario. Our nose gear location was also our first one set. It was set at 12 feet back from the nose of the aircraft. This was because it was our closest structural member that could support the loads experienced during an emergency brake. Using the ratio, this set our main gear at 37.8 feet back from the nose. Due to the presence of our bomb bay and engines inboard of our main landing gear, our landing gear was set out at 21.3 feet off the center line of the aircraft. We selected a 4-tire layout for our main gear. This was because it allowed us to reduce the size of our tires overall, which reduced the size of our landing gear bays, which allowed us to not add any bumps or disruptions to the smooth contours of the aircraft and preserve the stealth capabilities. Our nose gear was kept with the 2-wheel configuration, which allows for good steering capabilities, and ended up at 40 by 50.5 inch diameter tires. This video briefly shows how we are folding our main gear to reduce the overall height of our loading bay with the smaller tires, 4 tires on each main gear. As you can see, the tires fold up flat against the strut, which reduced our overall height in the folded configuration. For our landing gear, we looked at critical angles and critical weights. Our first critical angle is the tip back, the point which the CG crosses over the static ground line. We set this at the minimum allowed 15 degrees. This was in order to increase the height of our plane off the ground for easy removal of engines and easy loading of the payloads, without actually having to lift the aircraft off the ground to achieve either of those. This ended up setting our tail strike angle at 10.9 degrees. This is higher than both our takeoff angle and our engine blanking angle, meaning there has to be 2 failures before we will ever strike the tail on the ground. Our turnover angle is exceedingly low at 31 degrees. This is due to the very wide spread of our main gear due to the presence of bomb bays and engines inboard. As I said before, our max takeoff weight is 284,300 pounds, but we can sustain up to 307,100 pounds and still perform a takeoff abort before experiencing tire failure, and we can sustain a max static loading of 316,700 pounds before tire failure as well. I will now pass it over to Van Pollard for our cockpit and defense systems.
Thank you, Nick. So our cockpit is designed to accommodate both a pilot and a co-pilot. It's largely based on that used within the B-2, which is our closest mission-based comparable. Due to the very long mission durations of our aircraft, pilot amenities include a lavatory, bed, and microwave. ROSCOM outlines several FAR requirements for pilot visibility: a 20-degree field of view from level sight up, a 15-degree field of view from level sight down, 135 degrees from central line output of the aircraft, and 30-degree field of view from center blind inboard of the aircraft. These images here show that we are in full compliance with all regulations outlined by ROSCOM. In addition, our cockpit utilizes the ACES 5 ejection seats. These seats are operable from speeds anywhere from 0 to 1,000 feet per second and at altitudes up to 60,000 feet. This image shows our egress process. These yellow panels indicate the portion of the aircraft surface which will blow off to allow a safe exit path, and this would occur at the same time as the seat slide back. Our aircraft utilizes 2 main radar systems, the first being our primary, which is based off the AAMQ-181. This is a low probability of interceptor radar and is also ground compatible. The second radar system is the ANALR-69V. This is the radar warning receivers whose receptors are spread out across the surface of our aircraft, which also produces favorable results for our low observability. This system is ECM capable and is the one currently used aboard the C-130. So the main mission parameter, or pardon me, design parameter of our aircraft is stealth. The idea is not to be seen. However, we'd be remiss if we did not put some defensive measures. Our aircraft comes with two primary systems, the first of which being the High Energy Liquid Laser Area Defense Systems, or HELIDS, designed by General Atomics. These directed energy systems utilize a 150 kilowatt laser to execute a soft kill on any radar-guided ordnance targeted at our aircraft. We have 4 modules spread out across the aircraft, each equipped with their own lithium-ion battery that can be recharged in flight with excess energy from the generators. In the event that we are locked onto by an infrared seeking radar, the aircraft is equipped with 508 MJU-23B flares. These flares are of the same class that are used aboard the B-1 Lancer currently and are stored in 2 separate compartments behind each of the bomb bays. I will now pass it back to Max for our conclusion.
Thanks, man. Okay, so getting to the conclusion, we do have a few project risks that we'd like to talk about. First is the Warband FX-8080 airfoil. This airfoil is not used anywhere else. As such, we will do a little bit more wind tunnel testing to prove the design that it's a great airfoil to use. The advanced composite, the Perseus material, is currently under NASA development. Right now, it's undergoing structural testing. It has a very high technology readiness level, pretty close to being done, and it's designed for a long-range craft similar to ours, a heavy lift body and a flying wing. The HELID system also is currently in testing for the military and is a patented product. This, furthermore, needs a little bit more testing to prove the design again. Lastly, of course, we have integration risks. Every aircraft does. As part of this, in order to mitigate it, we'll do more testing along with the aircraft as it is produced. And finally, we have our compliance. So we are compliant with all of our threshold values for the aircraft, all the way from our unrefueled range going down to our landing ground run. Any questions?
Steve, you want to start?
Sure. So I'm glad that you addressed the risks at the very end. That was good. And overall, I thought it was a very well polished and professional presentation. So nice job. You guys were all well spoken. Did a good job presenting. I think for material that, I mean, it's a lot of work presented in a little bit of time. I think you guys did a great job in that. I like the animation. Helped me understand what it is that you're trying to say. I think it was an effective use in your presentation. It was sort of like seasoning it just a little bit, not too much, but enough to make it interesting. I'm really curious about why you chose to exceed the requirements for the payload by about 5,000 pounds. A couple questions. One, how does that impact your empty weight? And 2, how does that impact your cost? And 3, what is your stakeholder, your customer, think of that requirement? Because you'd be surprised at how, at least in my experience, how much the increase in costs due to, what is that, about 5,000 pounds is a pretty significant chunk of your payload. So, any thoughts on that?
Okay. Basically what happened was I wanted to compare it to the B2. We started with a 30,000 pound limit initially to carry the GPU, which is the heaviest ordnance that we can carry, and then sized it up from there for maximum payload. As far as I know from what I did my reading on, the B2 has a very similar payload fraction. It's either 40 or 45 depending on the source that you read. And I wanted to be able to carry at least 40,000 pounds. Realized if I wanted to be able to do that and carry rotary launchers, I need to carry 5,000 more. So adding the weight does cost more, but it allows us to vary as much as we can. That's the basics for why we decided to choose it. The cost increase, because we use a similar design to the, like, the bomb bay is based off of the Nighthawk, B2, and several other designs. Basically with the keel, we didn't really have to add that much weight to it to make it so it worked. The 40 to 45,000 pounds didn't really change the structural weight much at all as far as the aluminum went, so it didn't cause a cost increase. I know that like increasing the 5,000 pounds is a problem and it does increase the cost, but the design that we already had forth supported the weight without any changes.
Did you do a cost comparison?
No, I didn't do it.
I think you'd be shocked at how much of an impact that has on your
Yeah, I didn't have to change the design, so it seemed to be okay, but again.
So you guys developed the requirements, or were they customer based?
We developed it.
Okay. So
It was based on the current one, the V21 project. It was based on kind of the requirements that we figured they would have. Just kind of speculation. Just trying to keep it as a reasonable business case and something that would be sort of competitive in that project.
So be very careful when you go out into industry about exceeding requirements.
I have one of the things to say too.
Because you might think it makes you competitive. It maybe does in one aspect, in the performance aspect, but in other aspects it might be a detriment.
Other thing was one of the main weapons that we had, the Mark 84s, carrying the maximum that the rotary launcher allows you is right up at the 40,000 pound minimum. Rotary launchers are about 2,500 pounds a piece, so 45,000 pounds made it so we were under that weight. If we were like minimally compliable, it's something like 44.7. So 45 is a nice round number to go to. That was the other main reason why I went to that.
The engine performance has me a little concerned. I think it was slide 25. It shows you're right on the edge of the established data. Therefore, you should be fine. It seems to me like that should be a project risk, a risk buy-down approach for that. You'd be amazed at how these charts are developed with these curves. Just because the curve says you're right there, and going into region 2 means to diffuser design methods needed. You could be adding a lot of risk to your project by going right to the ragged edge of these charts. You kind of want to stay away from those in design practice unless that's the purpose of your activity, is to push the boundary for that particular performance parameter. You kind of want to stay away from those edges. You may or may not be safe there. One other thing, stability control. Let's see, page 63. Wait, no, sorry. There was a chart that showed the
Stability criteria?
Actually, yeah, this was one too. So I would say, I think the statement you made was that you're good out to 90 degrees angle of attack for pitch stability.
Yes.
I would think very carefully about that statement beyond about 2 degrees angle of attack, because you see it goes positive CM alpha between 2 and 3, and then it goes negative again, and then it goes positive, and then it goes negative. So I'm not sure that I think you need to think very carefully about that statement that you're going to go beyond 2 degrees angle attack.
The other data that we had that we didn't have room to publish, if I had taken an average of all of them and put the data all together, it would have showed it. So I just chose not to do that. That's why.
Thank you. Well done.
Yeah, I thought it was overall really good. There was one nitpicky thing I found that kind of happened throughout the whole presentation, just attention to detail on how you mark your charts. So like here you have angle of attack, you spelled out degrees, and then you'd also put a DG. And you do the same thing with like your C in the M next to it, or C, or its subs. Like just little things like that. You want to be looking through that. I know it's really nitpicky, but you just want to look out for things like that. Other than that, nothing like not that bad throughout the whole thing. When you guys were talking about using perf, you might want to mention what that is, because I know what it is because I just used it like 2 years ago, but there's people that won't know what it is. And then on slide 32, you mentioned with zero payload, you said something about EW. I'm not really sure if that's necessary unless you guys actually have a mission for EW. So do you have a mission for electronic warfare, or?
Technically, we could. We haven't really outlined one yet, but it's something, being a versatile platform, we could implement that. It's something that the B2 can do, and we just haven't looked a whole lot into it, and there's not a whole lot out there available. So we don't have one set up right now, but it's a possibility.
Yeah, so maybe earlier on, you mentioned that as something you're looking at doing as other options for your platform, not just throwing it randomly out there. It kind of happened later on too. You mentioned the directed energy weapons at one point earlier on, but it hadn't been said at any time beforehand, and you might want to mention that up front, so it's not just like a curveball in the middle of the presentation, and then you see it finally at the very end. And then, so you actually talked about the risk duty of that. Let's see that. We already talked about that. So, nope, that's good. It's all right. You guys answer stuff at the end. Oh, so when you, on slide 73, you guys were talking about how like the amenities, and it seems kind of silly. But you talked about how it's a bed, like all that other stuff. How many aircrew do you actually have on board?
Just 2, sir.
Just 2, so you might want to check that. I think the Air Force requires 3 if one's going to go off the station. So if one wants to sleep, for whatever reason, I think one has to take over. Not totally sure on that, but I'm pretty sure. Because I know the C-17 has something similar, and they have 3 pilots. So just something to think about. I mean, just little things. But overall, I thought it was really good, really interesting. I saw your presentation last year, so I was kind of curious to see what you guys came back with. I thought it was pretty good. Good job, guys.
Thank you. Thank you. Okay, again, nice job. The animations I thought were really helpful, and all your graphics and everything were outstanding. I would have loved to see somebody pick this up and show me stuff, because you guys did a lot of work on that, and that's beautiful.
Thank you.
This classified package is awesome. But since I have it, I have to poke at it a little bit. Because I don't know if you know this, you may or may not. There's no such thing as classified in terms of markings. You will never see a document that says classified across it, only in movies. And you're not allowed to actually mark these the way they're supposed to be, because then they would be right. So you did the right thing. But just so you know, there's classification markings that are. Has anybody talked? Have you learned about this? Classification markings? Okay, there's a whole world of classification markings that are out there, and this paragraph has to have portion markings on it. This diagram has to have portion markings on it. It's all.
We just wanted to be funny.
And you know what? This was awesome, and I'm glad you did it. But since it was there, I had to let you know that world is out there. That's
like doing taxes.
You're welcome.
Right.
So at the very beginning, I would have liked to have seen something. This looks a lot like a B2. What is it? What are you bringing? Why don't I just buy more B2s? I didn't get a sense of what it is that this does that the B2 doesn't, and why I need your system over something I can just go buy more of. And so I think that might have been a nice motivation up front. How do you deal with compressor stall at heights of attack? You got your inlets up on top there. It sure seems like that would be a problem.
So we didn't really handle it. We did a conservative calculation on when it would happen. I calculated it to be about 10 degrees. And that was with just the flow separates immediately over the leading edge. So it's pretty conservative, but it ended up being above any of our operating angles of attack, so we just kind of left it there. I'm doing the propulsion minor, and we really haven't covered any of that stuff, so I don't really know how we would handle that. It'd be something that we would have to look into.
I think staying below your ankle's probably going to be the answer.
Yeah.
But just so you know that's there, and that's something to be worried about. On your thrust required curves, this is a little bit in the nit, but you made the comment, this was at, I forget what your weight was, if this was at full weight or something, at cruise configuration. Okay, when you make a data chart, you will be surprised at how long it will live in the company, and how many people will lift it and use it for other things. you have to have on this chart all your configuration stuff. You need to say, this is, it's not enough to say it in words, because somebody's gonna lift this chart and they're gonna use it in the wrong place some other time in the future. So be careful of that when you do this. Make sure that you're really explicit on that. Did you do any analysis to see what your tip deflection angle would be at max Q and max deflection?
Like what angle our wings would be?
Yeah, so you're flying along and you deflect and the tip rotates.
Oh, no, I didn't do any rotational stuff. I mean, technically the spars are loaded differently, but it's not the accurate loading.
So
no.
It's worth looking at, because one of the things that can happen is you deflect your control surface and you get so much deflection that you'll get control reversal. So you think that you're taught to go one way, and then because of the deflection, you actually get control reversal, and that's worth looking at to make sure that that doesn't happen. Your mismatch in Reynolds number on your drag polar. This always happens. Your data, which is fine. Does the Reynolds number fully explain why your drag polar is off?
So
do we really believe that that's?
There were a few things that we were concerned about. We had some issues with manufacturing. The model came out a couple times incorrect, so there's a lot of putty there that you can't see. Not sure the airfoil came out the way we wanted it to. So it's a mix of Reynolds number and manufacturing, some calibration issues potentially with the sensor, but I didn't want to kind of delineate all that.
Well, that's fine. So the direction of your mismatch, is that consistent with your Reynolds number difference?
I would, so, hold up here a second, but I don't know.
So your Reynolds number is lower.
Right, so I would expect to see kind of those higher CL values flatten out a little bit more. As you hit that turbulent flow field, you have more momentum in the flow field. You should have less separation, less drag. I tried to do the Reynolds number extrapolation on the data, which is why you kind of see it goes from basically straight up to sort of more flat curve here. Yeah. But it was just not quite what is actually happening.
The CM alpha being unstable between 2 and 6 degrees was noted. Okay, so let's say that actually is the case. So what? What does that do to you? To the flight controls engineer who's got to design the autopilot.
That makes the system have to work a lot harder.
Okay. Seeing data like this is not uncommon. I got systems that do this kind of stuff, and you get all kinds of weird things and all of. And what ends up happening is you've got your flight controls guy then has to schedule his autopilot across angle of attack. So I need different gains at 2 degrees than I need at 3 degrees. And so the fact that that's doing that doesn't bother me, but you just need to know that your autopilot guy is gonna have to deal with that, and that's one of the ways you deal with it.
Think of it as full employment.
Sorry?
Think of it as full employment for the
That's right. Controls guys love that. Not really. So your handling qualities, you made a comment that you're level 1. You can go up the slide. You said that you're level 1 handling qualities, but I don't see data that supports that. What is it that made this level 1 handling quality?
I looked at the mil-spec requirements for basically maneuverability, and I went through the simulation until I could meet all of them.
Okay, are you familiar with the mil specs that have requirements on damping ratio and?
Yes. That's how I place the poles of the aircraft.
That's how you play. Oh, not when you place the poles. How did you place the poles? What are you talking about?
Well, in terms of the damping ratio and natural frequency and such like that,
okay.
I placed the poles of the aircraft such that those criteria were met in terms of damping ratio and
okay. How did you place the poles?
I used basically a feedback system with a K-matrix, and I placed them in desired places from where they originally were from our analytical solution.
Okay. What's your control architecture?
control architecture.
The PID kind of controller? is that-
Yeah, basic feedback. I didn't do anything too fancy.
Okay, and what do you feed back?
Feedback.
What's your feedback control log?
I'd have to look at it. I don't have it off the top of my head, but.
All right.
It was designed by our stability controls teacher, Dr. Mordinon. We took his, we did a project, which is where these graphs came from basically. We took that project and we modified it to handle our aircraft, and so we would test flight and be able to mess with those flying qualities and the damping ratios and the natural frequencies.
Okay. All right, well, if you're going to talk about flying qualities and handling qualities, we ought to relate it to the spec, not a time response.
Okay.
Because time response doesn't tell you that.
All right.
What are you doing for control allocation? When you say roll, how do you allocate that to your actual effectors?
Oh, we got like 3 minutes left.
Okay, I'm sorry.
This is first time.
We can talk about that later.
Okay. Because that seems very complicated.
I only have two comments. One is, depending on your customer, your airspeeds should be in knots. If you're talking to an Air Force customer, most of the time, Navy customer, they're old pilots. Those guys are not calibrated in feet per second. Aerodynamicists like Nikolai, and maybe your customer who was played by Dr. Crisler, like feet per second. So depending on your customer, you want to make your units in whatever units that guy dictates. And if he's saying feet per second, you did the right thing. But if you go to Air Force or military, they're going to have ex-pilots, they're going to want to see knots.
Usually I was leaning on them for pilot.
All right, all right. The last thing that I had was the advanced composite under development. I noticed that you mentioned it had a TRL of 6. There's quite a ways to go before you're ready to go to production with that. What you want to do is make sure that in your risk mitigation plan, you know what that technology maturation plan looks like. Make sure it lines up with your program development. If it doesn't, or if it looks like it's kind of dicey around the edge, then what you want to do is have some kind of a backup in place as part of the mitigation plan. So you have something there just in case this thing never gets off the TRL-6, or in case it totally crashes and you don't have the material available. So that's all I have. Good job, really nice job. Thank you.
I would open it up for questions from the students, but we really don't have much time. I have a couple of things to say in this teachable moment. The first one is, there are 2 words I don't ever want to hear any of you ever say for the rest of your professional career. That's bunch and stuff. Those words out loud in the presentation again. Remember I talked about having a concise statement of your design approach? Basically, you would take B2 and X47 concept, and you were just going to evolve those by switching, basically playing with the weight fraction, the payload fraction. Instead of that, you'd have answered all their questions and nailed them flat. Remember the thing about the Roskin summary chart? The big numbers? Yeah. Basically, you'd have had that right at the top. A lot of their questions would have been answered right off the top. I'm looking at my score sheet here, and it says things like really good, excellent, very good, super. I'm immensely proud of all of them. I think you guys ran into some snags back around Thanksgiving. You could have punted this thing, and you didn't do it. You came back in January and you fixed all these problems. You hung together as a team. You took care of each other. You picked each other up. I am immensely proud of all of you. I had something.
Thank you.
I agree with Dr. Crisler, but I want to poke you on the handout, which was really cool, like Scott said. But then you showed this chart up there with no markings.
15 yards.
Good one.
Awesome. Well done.